So we're going to go ahead and finish what we covered last time with zeros of polynomial. Okay? So we've done zeros of polynomial. We said if the remainder, we use the remainder theorem to determine the value of a function at a particular point. And of course, for any polynomial whose remainder is 0 by dividing by a linear factor, then that linear factor is a factor of that particular polynomial. Okay. So today we're going to talk a little bit about some rules called Descartes rule. Okay, let's go ahead and do that. So Descartes rules of science says let f of x be a polynomial an x n an minus 1 x n minus 1 plus ax plus a0. It says the number of positive real zeros of f is equal to the number of variation in sign of f of x or less than that number by even integer. What does that mean? So number of positive zeros of f is the number of variation of sign of f or less by even integer. Okay? Another way, say for instance, let's go ahead and do an example so we can illustrate this a little bit better. Say for example, let f of x equal, say, x to the 4 plus x cubed minus x squared plus x minus 3. Right? That's that polynomial. We know, for instance, if I want to know how many possible positive zeros of x, of f of x, then I can count how many times the sign changes in the polynomial itself. Okay? So for instance, this is a positive, right? This is a positive, no change, right? But in here we have one change because it went from positive to negative. From here it went from negative to positive, that's another change, right? And then it went from positive to negative, that's another change. Yes? So how many times did the sign change? 3 times. So sign change equals 3. So what does that mean? That means the number of positive zeros is at most 3. Yes? At most how many? 3. It says or well, less by an even integer. So there could be 3 positive zeros Or if I take an even integer from here, say 1, say 2, right? So 3 minus 2 is 1. So this particular polynomial could have 3 possible positive answers or just 1 positive answer. Clear? Is that understood? Yeah. Okay. So no matter what, it's always. So if we end up, say, for instance, with 5 variation of signs, then the polynomial would have at most 5 positive answers, right? Or could be 3, right? Or it could have 1. So those are the possible positive answer for a polynomial that has 5 changes in its sign. Okay. So we always go, whatever we get first, we go down by 2's until we get to 1 or 0. That's where we stop. If we end up with 1, then we know for sure there is at least 1. Yeah? Or more. Up to 5. So that is how many positive answers there could be in a given polynomial. Now, it also says the number of negative real zeros. Yes? So what are these? Number of negative real zeros specified is either let me write it exactly the same thing. Either the number of changes in sign of f of minus x or less than that by an even integer. So to know how many negative answers there are possible, we don't look at f of x, we look at f of minus x. Another way, we replace every x by minus x, and then we look at how many times the sign changes. So let's go ahead and take a look at another example. Let's say, for instance, again, f of x equal, say, x to the 4 plus, say, x cubed minus x squared minus x plus 5.
Can you check the camera back? I accidentally hit the camera.
You hit the camera?
Yeah.
Ah, you made Tom angry now. Let me see if we can fix it a little bit. If I can see what's going on.
Yeah, mine's it.
Here we go.
A little bit more to the side. Good. Ooh, go back, go back.
Here we go. Good enough?
Yes, it now.
All right. So now we are going to, and stop kicking the camera. All right. So we're looking at this polynomial now, and we want to know, we want to see how many possible negative answers are there. So we can see both positive and negative. Yes? Let's see first how many possible positive answers. So I'm going to put a positive over here, negative over here, and then we're going to decide how many positive possible in there, how many negative possible in there. For the positive, we just look at the polynomial itself. And then I count how many times the sign changes. Okay? So first the sign, it starts at positive, right? The next term is also positive, so no change in that. And then we go to negative, so that's one change between here and here. Yeah? From negative to negative, no change. And then from negative to positive, we change one more time, right? So therefore, this has two changes. So therefore, we can conclude the possible positive answers are either 2 or, if we go down by an even integer, so we go 2 at a time. It's either 2 or 0. Yeah, so this polynomial could have two positive real solutions, or it could have none. Yeah. Let's take a look at how many negative possible solutions there are. Yeah. Notice, by the rules we study, this should have at most how many? 4. Why? Because this is the most, this is the exponent with the degree 4. So in degree 4 polynomial should have at most how many? 4 solutions. Yes? That includes repetition and complex or imaginary number, non-real solutions. So let's take a look at f of minus x now. With f of minus x, we replace x by minus x. And it's simple and easy. If the exponent on the x is even, I just leave it the same. I don't change it. So x4, for f of minus x, it stays x4. For minus x in x cubed, because the exponent is odd, that sign change. So if it's a positive, I make it negative. If it's negative, I make it positive. So now plus becomes minus because we're looking at x cubed, right? For the x squared, it's even, so it stays the same. For the x, it is odd because it's 1. So we change it, we make it positive. The constant stays the same. No changes on the constant. So now let's take a look at this and see how many times did the sign change. Positive to negative is 1. Yep. Negative to negative, no change. Negative to positive is another one. Positive to positive, no change. So therefore, we have 2 change of signs, right? So therefore, the possible negative answers are simply either 2 or less by an even number. So we'll go keep subtracting 2 until we get to 1 or 0. So if I subtract 2 from here, I get 0 and I stop. Yep. Notice, what is the total possible answer you could have? 4. Now, if you get a 3 and 5 and 2 over here, say, hey, there's something wrong here. What? Because the total possible is 5, and it is what? But here it is an exponent of 4. Yeah, so we couldn't do that. Okay? Any question about the rules? All right. Let's go ahead and finish up with the next rule. It says upper and lower bound of the zeros. Upper and lower bound rules. There has to be, when we're looking for the zeros of a polynomial, we said we do what? We take all the possible zeros, yep, and we check them one at a time. There might be scenarios where we don't have to go all the way. We need to stop at one point. Yes? So for instance, if I have a graph like this, right? And let's say one of the possible zeros is here, okay? I know, for instance, based on the graph, any number after that, I really don't have to do what? To check. Why? Because I know on the graph, everything on this side is not going to do anything to me except getting me higher and higher, right? And say, for instance, so this point becomes the upper bound of those zeros. So in another way, I don't have to try any number beyond that. Okay? Similarly, if I'm here and I have numbers that possible zeros on this side, yep, I don't have to try any of them. Why? Because I know for a fact that after this point from here down, all I'm doing is getting more in the negative. Yes? It will be nice to recognize those numbers when we get to them. This is called the upper bound of the zeros. So I know beyond that there is no zeros. This would be the lower bound of the zeros. It'll be when we're looking at a picture or when we're looking at a graph, we can recognize where the upper bound is and where the lower bound is. Okay? But when we're looking at a polynomial function, we don't normally do right away. Okay? Last time we talked about one thing, we said, or basically in Descartes rules right now, we can say if, for instance, say f of x equal x cubed plus 3x plus 7. Yeah? When we look at the zeros, we say they are plus or minus 1, plus or minus 7. This is just a simple example, right? Now, here's one thing. If we look at the possible positive answers, now using the Descartes rules, do I have any change in sign? No. So that means all the possible zeros, all the possible positive zeros are what? Zeros. We don't have any positive zero. Why? Because we don't have any change of sign. Does that make sense? But based on this, we can say, all right, when I'm going to check for zeros, I don't need to try any positive number. Why? Because the fact that this polynomial doesn't have any change of sign, therefore, positive zeros don't exist in that. If I try any positive number, I'm just wasting my time. Does that make sense? And we can also check for negative real zeros by using the change of sign, f of minus x, and then we will see there is one possible negative x. Yes, but those give me some ideas. Does that apply only to the beginning of the parabola? No, it could apply somewhere in the middle. Let's talk about how do we do it. It says, say for instance, says if C is a positive number, if C is a positive number. Okay, what we're doing here, we're looking at, let me write it down first. We have f of x is a polynomial, and we're dividing that syntactically by x minus c. We're doing synthetic division by x minus c, okay? Using I guess I'm not able to write today. Using synthetic division. It says if C is positive, if C is greater than 0, it says if C is greater than 0, and each number in the last row when you do division, I say you have C here, right? You have your polynomial here, coefficients, correct? And then you do the division, and when we're talking about the last row, we're talking about the answers you get here. Okay? And if these numbers in the last row, positive or zeros, and each number is positive or 0. So let's see one more time. So I'm doing the C over here. C is a positive number, right? Let's say, for instance, I got a 3, 0, 5, 7 here. Yeah? And all of these numbers are simply, say, what? Either positive or zeros. Yeah? What does that mean to me? It means then C is an upper bound. Okay? Then C is an upper bound. It means whatever C is, and you get that numbers, don't try anything above that number, above C. So if C happened to be 1, and I ended up with this result, then, and there is a 2 in the possible zeros, I don't need to try 2. Why? Because I know 1 is an upper bound. There is nothing past C could be a 0 in there. We clear? This is if C is positive. Yes? Now, if C is negative, and the numbers in the last row alternate between positive and negative. With zeros, count as positive or negative. Really, zeros count as needed. If I need this term to be positive, then I can count it positive. If I need it to be negative, I can count it negative. Okay? Then C is a lower one. So for instance, this is my C. This is my last row over here. Yeah. After I do the division, I ended up with a 5. Say 5, negative 2, 3, negative 4. Yeah. What happened to these? These numbers are alternate. Yeah. Positive, negative, positive, negative. Yes? So that means the following. Nothing below C is going to be a negative. It's going to give me a 0. Okay? So C is my lower bound. So with the graph we did before, C here would be the upper bound for the positive. C here would be the lower bound for the negative. Okay? So another way, I don't try any numbers on this side, and I don't try any numbers on that side. So I'm going to stick with the numbers lower than the upper bound, but higher than the lower bound. Now, what does that mean for 0? For instance, if this happened to be a 0, yeah, and we have a positive here and positive here, right? Then I can count this as a negative. So that will give me the alternating sequence. If we have a negative here and a negative here, then 0 in this case would be counted as positive just to give me the alternating sequence. Okay? So 0 will take a place, and that place would be either positive or negative as needed. Okay? Let's do an example. Find all zeros. It says 6x cubed minus 4x squared plus 3x minus 2. And it says to list them all first and then find the zeros. Yeah? So let's do that. So first, let's list them. Do you guys still remember how you list those? Again, this is your fraction. Yeah? And with that, factors of 2 are plus or minus 1, plus or minus 2. Okay? Factors of 6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4. Yeah? So I'm going to list them one more time. So what are the possible zeros? We use the 1 with all of these. So plus or minus 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/4. Yeah? These are all the possible zeros for the ones. When I go to 2, with all of these, we say plus or minus 2. Yeah? Now, 2 over 2 gives me 1. We already have the plus or minus 1. So we have plus or minus 2/3. That's a 2 over 3. And plus or minus 2 over 4. But 2 over 4 is the same as 1/2. So we got the 1/2 here. So I don't have to repeat that. Okay? So let's take a look at dividing by 1 first. So if I check 1, what do I get? So we have 6, -4, 3, -2. So I'm going to take the division down. So I'm going to take 6 down. So that's 6. 6 times 1 is 6. That's going to give me a 2. 2 times 1 is 2. And that's going to give me a 5. 5 times 1 is 5. That's going to give me a 3. Okay? That's not a 0, is it? But notice, all of these numbers are what? Positive. This one is positive, so I don't need to try anything above 1. So another way, plus or minus 2, which I should have plus 2 over here, I can just eliminate that. It's not going to be a possible 0. Okay? So one of the zeros will be 2/3, and then you can go ahead and factor that. Well, this is just an example to show the upper bound and lower bound. Okay. Clear on that? So if I had more than whatever, then say 2, if I have a 3 or 4, 5 or 6, all of these numbers, I don't have to try them anymore because we figured out that 1 is an upper bound, and therefore every number above 1 does not need to be checked. Okay. So that takes care of all the rules, regulation for zeros of polynomial. Any question on that? All right. So we're done with that section. This is the last section we're going to cover before the test. Let's go ahead and cover it. Rational function. So rational function are function of the form of px over qx, where p and q are polynomial and qx is not 0. So it is simply, rational function is function such that the p of x, the numerator, is a polynomial. Okay? The denominator is also a polynomial, and since the denominator is And the bottom we cannot divide by 0, so we have the exclusion that this number is not equal to 0, whatever it is. Okay? That's by definition. To find the domain of a rational function, domain of a rational function, always all real numbers except some values. Yes? Except what? We already decided that q of x is not simply what? 0. Okay? So therefore, except the values of x that make q of x equals 0. So we want to exclude those values. Okay? We wanted to exclude those values from the function. Okay? Once we do that, that's our domain. Okay. So if I have, for instance, if I have, say, f of x equals, say, 1 over x, f of x equals 1 over x. That's a simple equation. And we're trying to find the domain of that function. So I want to look at the domain. So domain is, we start with all real numbers. Yes? So I'm going to write it down. Equal R. R means all real numbers. We do have exceptions. Okay? Now we need to look at the list of those exceptions. Okay? We need to find the list of those exceptions. What exception do I have in this case? Q of x not equal to 0. But this is Q of x. When this value is 0, what value of x makes this 0? 0. Yes? So therefore, we want to exclude 0. So now I can substitute any value for x I want, except 0. We cannot have 0 here. How do I write this in interval notation? Well, all real numbers go from negative infinity to positive infinity, right? But we do have exception in the middle. If we don't, then it's a negative infinity to positive infinity. If we do have exceptions, I'm going to start with a negative infinity, right? And I'm going to write the first exception I'm going to hit on the number line. Since the only exception is 0, so I'm going to go up to 0. Yeah. Union, open parentheses. Now I'm going to start from where I left off. I left off at exception 0 all the way to infinity. So that means the domain is used from negative infinity to infinity, and we excluding 0 in the middle. That's where we use the parentheses to exclude that number. So I'm excluding 0 from the left. I'm also excluding 0 from the right. Does that make sense? Yeah. So on the number line, If this is my 0, this side says you go from here a little bit before that. And this side says you start a little bit after 0 and you go straight. So therefore, this is my real. Now, what if I say x minus 1? How does that change? Then my exception will be not 0 anymore, it will be 1. So this one will change. Instead of 0, I'm going to put a 1. And here I'm going to take the 0, put 1, put 1. Simple as that. Yeah? Any question? All right. Let's make things a little bit tiny bit harder. Suppose we have f of x is x over x squared minus 1. How do I find those zeros? Or how do I find those exceptions? Well, simply to find the exceptions, notice, I don't care what the numerator has. I don't worry about it for those exceptions. Okay. So what I worry about is the denominator only. If you can't figure it out right away what they are, just take the denominator, which is x squared minus 1 equals 0, and solve that equation. So that gives me x squared equal 1. So that gives me x equal, we're going to take the square root. Remember, every time we take the square root, we do what? Plus or minus, yes? So that's going to give me plus or minus 1. So there are two values for which I need to exclude from the real numbers. If I want to write it down, it will be r, take away, negative 1 and 1. This is one way of writing it down if you're writing it on a piece of paper. If you're working on my math lab or you're working on WebAssign, whichever one you're working on, they may ask you to write interval notation. How do I transfer this to interval notation? We start with always negative infinity. Yes? Now, as you go from left to right, which one would you hit first? The negative 1 or the 1? Negative 1, so I'm going to go to negative 1. Close that. Yes? Am I done here? No. Union. Now let's start. We left at negative 1. And the next number here would also be negative 1 because I'm only excluding negative 1, nothing else. So negative 1. If I go from left to right, which number I'm going to hit next? The 1. Union. Then we're going to go from, the last one would be from 1 to infinity. And this is how you illustrate the interval notation for that. So if you didn't have any numbers to exclude, with simply one interval, negative infinity to positive infinity. Yeah? But if you have one number, we got two intervals, correct? We got negative infinity to that number to positive infinity. With two numbers, I get how many? 3. So what do we expect with 3 numbers? 4. Number of intervals, always one more than the number of exceptions. Clear? Always one more. So if I ended up with 2 number of exceptions, I should expect 3 intervals. If I ended up with 5 exceptions, 6 intervals, and so on. Okay. Any questions about finding the domain? So when I do those exceptions, that means as the graph goes past, it's not going to hit those numbers because they are not part of the domain. Suppose we have a particular graph, a rational equation, a rational function that has exclusion at -1 and 1. The one we just did right now, yes? It doesn't exist at -1, it doesn't exist at 1. So this is my -1, this is my 1. Yeah? Graphically, if -1 is not part of the graph, it has one of two things. Either the graph gets close to -1 and never touches it, keep going, keep going, right? Make sense? Or for some reason or another, let's say this is it, the graph gets here, jumps, and continue from here. That makes sense? So those are the two possibilities when we have a graph missing a point. Either the graph doesn't touch that, it goes and it may continue from here. So this is one way where a graph really doesn't go into one, -1, and doesn't take one. So if the graph doesn't touch the line like this, we call that vertical asymptote. Yes? But if the graph has this, it's just simply a hole. There's a hole in that graph. Yeah? How do I know which one is which? How do I know which one is which? It says, if the graph, if f of x goes to infinity or negative infinity as x goes to a, what that mean? Notice what I put over here. We said the graph is approaching, getting closer to -1, right? But doesn't touch -1. Yeah? But clear? It's getting closer. But is it ever -1? No. That's what this means. That means the graph or x value is getting close to a particular point. We called it A. In this case, it was -1. What happened to the graph itself? The graph either go up continuously, right? So it will hit infinity, or it may be this way going down, and it will hit negative infinity. So if this is an asymptote, that means f of x either going to be going to either infinity or negative infinity. Then we say x equal a is a vertical asymptote. Okay? Well, horizontal asymptote is exactly the same. Horizontal asymptote is exactly the same, except it's opposite way. Yes? That goes, this is going on y, the other one goes on x. Yes? Let's go ahead and do that in calculation. It sounds a whole lot better doing it in calculation and determining which one is which. Okay? So for instance, finding the vertical asymptote. Consider, for instance, I'm going to use the following. Say f of x equal x over x minus 1. The vertical asymptotes are easy to find out. How do I do that? Just take the denominator. We just did that. Which ones are the possible vertical asymptotes? Are the exceptions. All the exceptions from the domain are your possible asymptotes. Okay. So possible asymptote x equals 1. Why? Because 1 makes the denominator equal 0. That's the only exception in the domain. Correct? Well, how do I know if this one is a whole or is it an asymptote? Simply take this one, substitute in the numerator. Okay? If you get a 0, it's a whole. If you get anything other than 0, it is an asymptote. Okay? So now 1 is exception. But if I take 1, I put it on top. Do I get a 0? No. So x equal 1 is a vertical asymptote. Clear? Does that make sense? Easy enough? I guess. Let's do another one. Suppose we have x minus 1 over x squared minus 1. We just did this, right? What are the exceptions? 1 and negative 1 and 1, correct? Okay. Maybe both of them are asymptotes. Maybe one of them, maybe none of them. Let's see if any. But these are the only possible ones. There's no other vertical asymptotes beside these. Is negative 1 a vertical asymptote? Let's try. If I put a negative 1 here, do I get a 0? Negative 1 and negative 1, I get negative 2. It's not a 0. Then x equal 1 equal negative 1 vertical asymptote. That's the first one. Let's try 1. If I substitute 1 here, do I get a 0? Yeah, 1 minus 1 is 0. Then x equal 1 is not a vertical asymptote. It is simply a whole. So another way, at the x equal 1, this is 1. When the graph gets to that number, it will jump. Like that. Simple and easy. The other asymptote, we call it vertical or horizontal asymptote. Okay, let's figure out how do I determine horizontal asymptote. Let's say f of x equal a n x to the power n plus whatever on there pm x to the power m plus whatever. I only put the term with the highest exponent of each fraction of each polynomial. Yes? So another way, there must be some other terms here, but all the exponents are less than that one. Okay? There must be some other terms here, but the exponents are less than that. Okay. So this is the scenario. What's the scenarios here? Here we have an exponent of n. Here we have an exponent of m. Okay? So the relation between n and m is three possible scenarios. Either n and m are the same, yeah? N could be bigger than m, or n could be smaller than n. Let's take a look at each one and see what kind of asymptote we get on the horizontal asymptotes. Okay? Scenario number one, if n smaller than m. So that means the exponent on top is less than the exponent on the bottom. Then is one condition, y equals 0 is a horizontal asymptote. Simple. So if I have, so anything. So for instance, if we're looking at f of x equal x squared plus 5 divided by x cubed minus 3, yeah? This line, y equals 0, this line is a horizontal asymptote. What's a horizontal asymptote? What does it mean? Well, that means at the end of the line, the graph either goes like this if it's coming from the top, or goes like this if it's coming from the bottom, like this, or like this. Okay? That's what it means. In the middle, for the horizontal asymptote, no problem. Okay? Now, vertical asymptote means the graph will never cross the line. Okay? Horizontal asymptote, however, it may. However, it may go like this. It may cross it millions of times. It doesn't matter. But what it is, at the end, it will go like that, along with it, from either side. So it only matters at the end. In the middle, we don't care. Okay? It's different than vertical. Vertical, if I have an asymptote here, that means the graph is divided in two parts. Part on this side, part on that side, they don't meet. Why? Because we have this line, the graph is not going to get to it. Okay? So when it either gets to it, it's going to go either like that. It doesn't do like that. Okay? But with the horizontal, it does. In the middle, not at the end. We clear on the difference? All right. So let's do, this is scenario number one. So it says, so all the graphs in which the exponent on top is less than the exponent on the bottom, your horizontal asymptote is your y equal 0. Okay? Now, scenario number two, if n equals m. If n and m are the same, then your asymptote is and the coefficient of the top one divided by the coefficient of the bottom one. That would be your asymptote. Is a vertical or horizontal asymptote. Let's go ahead and take an example. Suppose we have f of x equal negative 2x cubed plus 7x squared plus 3 divided by, say, 3 x cubed plus x minus 1. Okay? So that means if I were to, for some reason or another, I need to graph this, I know the graph has a horizontal asymptote because those two exponents are exactly the same. Notice, I'm only looking at which one? The highest exponent in both. Yeah? Now, we know there is a asymptote because based on this condition, that meets that condition. What is the asymptote here? Asymptote y equal, first coefficient is -2 divided by, this coefficient is 3, right there. So that means if I go to the line, let's say this is -2/3, this line is an asymptote. Usually an asymptote we designate it by a dashed line. Okay? Again, what does that mean? The graph, if it's coming from here, and then it's going to go along like this. Yeah? If it's coming from up, it's going to go along like this. And on the other side, it's the same. Okay? So this is the horizontal, this is another horizontal asymptote. So what has left? We left with one condition. Yeah? That condition is n bigger than m. So if n is greater than m, n is greater than m, then no horizontal asymptote. So in this case, we will have no horizontal asymptote for that particular graph. Okay? Example, just let's say make that, if I make that a 5, this is 5 bigger than x cubed, x is a 5 bigger than x cubed. This particular equation has no horizontal asymptote. Any questions? So now in general, it says the graph of x has vertical asymptotes at all zeros of, in this case, we have qx, which we wrote down, and then they have the dx for the denominator. That's the only places where possible vertical asymptotes would happen. And then they give you all the condition again on these ones. Okay? Let's take some examples. It says, find all vertical and horizontal asymptotes of the graph of each rational function. So let's take a rational function. Okay, we have 2x squared divided by x squared minus 1. So we need to find all asymptotes. For now, we're only talking about horizontal and vertical. We're not talking about any other asymptotes. There are other asymptotes, but for now we're talking about these. Yeah? How do I find vertical asymptote? For vertical asymptote, set the denominator equal 0 and solve for x. we're going to take the denominator. We're going to set it equal to 0. We're going to solve for x. Okay? So we're looking at x squared minus 1 equals 0. X squared equal 1. X equal plus or minus 1. Yeah. Again, we said those are simply possible. Those are simply possible asymptotes. We also need to check them if they are. Okay? So let's check those. Is x equal 1 an asymptote? Is x equal 1? Is that an asymptote? No? Why? How do I determine if it is or it is not?
Yes.
Yes. We're going to substitute in the numerator, right? For now, we're going to substitute in the numerator.
It's not 0.
If the numerator doesn't give me zeros, then this is what? So we have x equal 1 is vertical asymptote. Yes? How about negative 1?
Yes.
It is a vertical asymptote. So in this particular example, both numbers happen to be asymptotes. Yeah? Let's take a look at the horizontal asymptote. For the horizontal asymptotes, we need to look at one thing. The highest exponent here, the highest exponent here, right? And deal with those only. These are the highest exponents. Yep. What condition do they meet? From the conditions we just wrote.
Beta sign. Beta sign.
Are they greater than each or the same?
Equal.
Those two exponents are equal, right? If they are equal, then I only look at the coefficients, yeah? And y equal, what's the coefficient on top?
2.
Divided by, what's the coefficient on bottom?
1.
So 2 over 1 is 2. So y equal 2 is your horizontal asymptote. Clear on that? Let's do another example. Another example, say, for instance, you have x squared plus x minus 2 divided by, say, x squared minus x minus 6. Okay? Let's go ahead and determine all the vertical and horizontal asymptotes. Now notice, for horizontal asymptotes, we can tell it right away, right? So what's the horizontal asymptote?
1.
Y equal 1. Here, there you go. Yeah? It's either going to be the coefficient or 0, or none. Nothing else. Those two are the same. The coefficient is 1. We're done. We got half the credit. So let's take a look at vertical asymptotes. To do vertical asymptotes, we're going to take this thing. We're going to set it equal to 0. We're going to solve. So the bottom number or the denominator is x squared minus x minus 6 equals 0. We need to factor that. We need to look for two numbers. When you multiply, you get a negative 6. But when you add them, you get a negative 1. What are those two numbers?
3 and 2.
3 and 2. One is positive, one is negative. Which one is the positive?
Negative 3.
So we have a negative 3. positive 2, right? So now we have two possibilities for zeros, right? First possibility is x equals 3, correct? What's the second possibility?
X equals -2.
Negative 2. Or both of these are asymptotes. Let's see. I'm gonna check 3 over here, right? So if I put a 3 over here, what do I get? 9 plus 3 is 12. Yes?
10.
12 take away 2 is 10. So that is an asymptote, right? So we know x equals 3, vertical asymptote, right? Let's check negative 2. Negative 2 square is 4. 4 take away 2 is 2. 2 take away 2 is 0. Is that a vertical asymptote?
No.
No. So the only asymptote we have is x equals 3. So that means this graph has something like that. At x equals 3, 1, 2, 3, we have the graph doesn't hit that line, right? But at negative 2, so negative 2 over here, wherever this line meets the graph, let's say it does over here, what's going to happen? You're going to have it like that. Yeah? So this is technically what that graph looks like. Any questions? No? Okay. I think this is all I'm going to cover today as far as